I'm looking at you through the glass. Don't know how much time has passed. Oh God, it feels like forever, but no one ever tells you that forever feels like home, sitting all alone inside your head.
Good evening, folks. I do have more revelation to present to you this evening, or this morning if you're watching. And honestly, this is all falling into place. If you've been keeping watch on my videos, you'll understand how I resolved the heavens, how the refraction creates the inversion. I simulated that in 3D. How the phi ratio, the golden mean, plays into the actual shape of the interior celestial glass spheres within the Earth. Their sizes, how the sun and the moon orbit within those spheres, how the planets operate. And since I've been on the topic of glass and refraction, of the 4 concentric glass spheres, we have the 100-kilometer glass sphere. Then higher we have what I call the moon sphere. Then higher still, or smaller still, we have the sun sphere. And then finally we have the celestial sphere, where the stars are contained and the celestial ocean is contained, and where the octahedron resides. And I had to figure out, it was trial and error, working with refraction in 3D, placing the sun and the moon in their appropriate spheres. Excuse me, I'm really tired right now. And try to figure out the size relationship, the amount of index of refraction for each sphere. It was tricky, and I resolved it. I finally figured it out, and it had to actually employ a negative refraction for one of the spheres. And now, for the first time in the public circle, you guys are being educated. This disclosure is big. I mean, for the longest time we've wondered why we had this association of lunacy with the moon. Lunatic, loony. And I can tell you right now, there's a very good reason for that. That is because the moon lies to us. The moon resides in its own glass sphere, outside of the sun sphere, which also includes the planets. The planets and the sun share the same sphere, that area, just outside the celestial sphere. But then there's another wall of glass, or sphere of glass, and then there's the moon section. And that interior of that section, there's an inverse scale relationship at play with proximity. Meaning, you know how we see the apogee and the perigee of the moon. When the moon is really big, we call it the perigee because it's supposedly closer to us. You see where I'm going with this? It's the exact opposite. When the moon is closest to us, it appears the smallest in the sky. When the moon is farthest away from us, in other words, when the moon is closer toward the center, it appears largest. That has to do with the negative refraction within that moon sphere. I'll show you that. And so now I have to edit my moon video that I created 2 years ago. I have to actually flip-flop the perigee and the apogee. And then we have to understand how the tides are actually being created now. It's not because the moon is closer to the Earth that it affects the tides more. It's actually that the moon is closer to the center, and it's pulling with it the 100-kilometer glass sphere, and that's what's causing the relief. That's what's causing the tides. And so I'm like 95% certain this is how it's working. This is how it's situated. And also too, how I played around with the scale of those two interior glass spheres, the moon sphere and the sun sphere, fit perfectly with the phi ratio curve. Perfectly. So I think I'll just show you that right now. It's pretty amazing. Let me pull up my screen share. I'm nearsighted. I got my contacts out. I'm going to have to look really close at the screen here. 1 second here. Bear with me here. I thought about like doing a little edit compilation, but I think it's just better if we do it on the fly. At least most of it. Okay. Let's pull that up. As you see, I altered my phi ratio graphic slightly, and you see the blue sphere, the blue section, that is the moon sphere, and the yellow section, that is the sun and planet sphere. And look how they are proportional to the phi curve ratio. I mean, it's perfect. You got the little interior of the phi curly Q going right in line with that for the moon sphere, and then you got the actual convergence of the spiral going right through the sun sphere, or almost. It's probably going right through, but I just haven't fine-tuned my calculations, but I can almost guarantee you it's going right through it. So I had to, here's the sun over here. It's about, well, I have it roughly, it's a little bit closer to the celestial sphere from the center. And then I put the moon right here. And the moon is about in the middle of its own little sphere. So what you have to realize, or what I had to realize, because I made the assumption or the declaration, I still believe very strongly that the moon and the sun are the same physical size, because I believe they were two halves of one sphere. And so I retained that hunch when I started doing my calculations. And so let's pull up Lightwave here. Here we go. Okay. Let me let's see how much my screen is showing here for you guys. Alright. Let me capture more of my screen. There we go. Okay. So let me go to my top view in wireframe mode, and I'll zoom back out a little bit. It's going to be a little bit difficult to see what's going on here, but hopefully I can demonstrate what I'm talking about here. Okay, so don't want to do that. Okay, let's zoom in there. Now we're looking from the top, and my camera's at the bottom, so that's where our viewer would be. So that camera would be at the equator looking toward the center of the Earth, and our view is from the top. Keep that in mind. So we have the sun and the moon in their own spheres. Let me zoom in real close. You see that right there? Okay, there we go. Here is the sun, and here's the moon. What I had to do was create different indexes of refraction for each specific sphere. Now, the glass sphere for the celestial sphere, the refraction for that, it didn't matter, because the sun and the moon were in front of it. So I was really just concerned about the spheres in front. And so we have three of them. We have the sun sphere, we have the moon sphere, and then we have the 100-kilometer glass sphere, very close to the Earth over there. And let me pull up my surfaces here. I call this one small glass would be the sun sphere, medium glass would be the moon sphere, and then big glass would be the 100-kilometer sphere. And you notice there's different levels of refraction. The 100-kilometer sphere has an index of 5. The medium glass, which is the moon sphere, has an index of negative 1.5. There is the negative. That's what I had to utilize in order to make it work. And I'll show you it works perfectly. And then the small glass would be the sun sphere, and that has an index of 1.25. And so I had to just play around with the parameters there. And let me go to my camera view and turn on the VPR. And go to, oh, let's bring down the focal length a little bit here. That's camera 2. Oh, what's happening here? 1 second, guys. Let's close out of here. And I'm going to reopen this because I think it messed up my settings. 1 second. Reopen. Load. Okay. There it is. There we go. All right. So I went to my camera view, and what I ended up doing was, let's bring our focal length down. Let's say 400 millimeters. There we go. I adjusted the refraction of the glass spheres in order to equalize the sun and the moon, because the sun and the moon are virtually the same angular diameter, about 30 arc minutes, which is 1/2 of a degree. Now the moon will fluctuate in size anywhere from about 29 to 33 arc minutes, and the sun will fluctuate, I believe, anywhere from, oh, I want to say 30 to 32 or something like that. It's a little bit tighter. And initially I played around with it. I had the moon and the sun in the same sphere. Obviously that didn't work. So it needed to have an inversion of the refraction at play. The moon had to be in its own separate sphere. And that's what I ended up doing. And so the funny thing about that, though, is that because you're utilizing negative refraction, let me select my moon here. I forgot what layer it is. 1 second here. The moon is going to be there, layer 5. Okay. So we go to my camera view again, and I have the moon selected. And if I move the moon farther away from the camera, it enlarges. If I move the moon closer to me, closer to the camera, it shrinks. Now I could show you that. Right now we see it very small in the camera view. Now I'll go to my top view and I'll show you where it's located. See right there on the bottom? I don't know if you can see that. Right there. Let me zoom in. See how close it is to the glass now? Before it was over here, and it shrunk in size. And so that's why, that's how the sun and the moon appear the same size, and they actually are the same size even though they are at different distances from the viewer. The moon is in its own negative refraction zone, which inverts the proximity and the scale. It's wild. It has an inverse proportional relationship, proximity versus scale. And so that's the trick. That is the, well, that's just another divine ruse, I guess you'd say. And so what I also needed to do now was figure out how the planets were exhibiting such a vast scale relationship as well. Now, if I go into Stellarium here, you're looking at Venus right here. Venus is transiting, and there's an occultation on the. There was an occultation June 6th, 2016. You probably remember that. There also was a transit exactly 4 years earlier on June 12th. I'm sorry, June 6th of 2012. And so, obviously, when Venus is in front of the Sun, or when Mercury is in front of the Sun, it's closer to us. It has a closer proximity to us, and it appears larger in the sky. If you look at the apparent diameter of Venus while it's transiting the Sun, it's 57.8 arc seconds. Now, if we go back to 2016 and we read the apparent, and we can't see Venus because it's behind the Sun, but it appears a lot smaller. The apparent diameter is 9.6. So we have just about 10 arc seconds to, what did I say, 58? Yeah, about 58. So about roughly a 6-to-1 scale variation. And that's huge. It's like, wow. I mean, the heliocentrist would conclude that they would base their Venus's orbit or its proximity to Earth based on those angular sizes, not taking into account the fact that they are being altered via refraction through glass. And that's exactly what's happening. As you have probably seen before, in a previous video, when I made this diagram here of the planets, well, it's hard to see, I don't have them here, but they had to fit behind, most of the planets had to fit behind the Sun. So I had to fit like Mars, Jupiter, Saturn, Neptune, Uranus, and Venus and Mercury when they go behind the Sun, as well as Venus and Mercury over here. So there's not much real estate here for these planets. Now, keep in mind that the planets are really tiny. I mean, I measured out the Sun, and I'm not quite, I haven't really solidified the exact width of the Sun. It's about 9 miles, I would say. Maybe a little bit bigger or smaller. But obviously the planets are going to be considerably smaller than 9 miles. Because when we see the transit over the Sun, we realize that wow, they're pretty small. Pretty small indeed. So we have room, but then we also have the moons of the planets, and so I had to squish their orbits to actually conform to their field, their limited field here, their truncated field. And so that's what I did. So I took Venus for a case study, and it works out really, really well with the refraction at play. Let me find Venus real quick here. Venus. I'm really tired right now. Okay, no, that's not Venus. There. Okay. So let's see if I could show you where Venus is. Okay. Right over here. Now what I did also, I went into Stellarium and I figured out, I calculated its right ascension based upon the relationship with the Sun, and I found out that it went like 40 some odd degrees to both sides of the Sun. And so that's what I did with my animation. I just animated Venus going around the Sun. You see it's right over here right now. It's kind of hard to tell. That would be its extremity to the left, and then let me hide these windows here. Its extremity to the right, and it circles around like that. I have it going in back. It's behind the Sun right now, and here is where it's in front of the Sun, so in the front of the Sun. So at frame 90, that would be the transit. Let's put that at frame 90. And then at frame 269, that would be the occultation. Actually, I moved it to the side so we can see it. So it's like one frame over. So right here, you see that little pink dot? That's during, it's right before an occultation. And you can see how small it is. And if I go to the transit, it's much bigger. Now if I were to turn off refraction, I'm not sure if I can, it's going to probably blow it off the screen here, but you turn off refraction, and then obviously it shrinks everything, and so I'm going to have to increase my focal length to the camera, make it even bigger, 1200, let's try 2200, let's try 3200. Okay, so you see it, you see the pink dot there during the transit, and then let's go over here, and there's the pink dot over here during an occultation. They're exactly the same size. There's no, even though this dot right here is farther away from us. I mean, obviously I got a 3200 millimeter camera. It's going to be the same size without any refraction. And so you don't need this huge million-mile orbit to exhibit the difference in scale from a occultation to a transit, or from an apogee to a perigee for that matter. It's exactly the same. So let's turn back on refraction after I put my camera back to a more comfortable focal length, and we see how it changes. Transit, occultation, perfectly resolved. So all the planets and the planets' moons are doing these orbits that are truncated, looking top down from the celestial sphere. And so there's my orbit of the planet video. Here it is. Or this is better yet. We'll show the glass spheres again. So we have these two glass spheres along with the celestial sphere and, of course, the 100-kilometer sphere. We have four spheres that create the cloaking sometimes that the moon shows us when it's part of the darkened part is cloaked and we can actually see a star behind it. But then the planets, and these are all mapped out according to stellarium coordinates, and they're all working perfectly, and I included the yellow line, the glass spheres, and they all work out fine. See, this zone here with the sun and the planets, actually it's this whole zone, this whole glass zone, it has positive refraction. So if an object is closer to the glass or closer to the viewer, it's going to enlarge. If it's farther away, it's going to shrink. It's going to do this drastically because of the refraction in this zone. This is the moon zone. It has negative refraction, and so it's going to do the exact opposite. When the moon goes toward the center, it's going to enlarge, and when it goes toward the glass, it's going to shrink. So the moon lies to us, and that is the big mystery of the moon. That and also the moon illusion, how it's upside down at the horizon. It's literally viewed inverted at the horizon. So I have to redo my moon video. I have to flip-flop the perigee and the apogee. So when the moon is actually close to the Earth, it's the apogee. It's the apogee in physical placement. You can call it the perigee because it looks bigger, but it's really it's farther away from the Earth. And so how the tides work, the tides are simply going to be lifting the 100-kilometer glass sky with the moon as it's drawn to the center. Let's see if I can find that really quick. There we go. So, and also this video is 2 years old, and obviously I got to put the moon and the sun closer to the center, and I'm My model is more streamlined now. But so when the moon gets drawn closer to the center, right, it appears bigger, but it's going to draw with it the glass sky, because there's magnetite in the glass, and the moon has a it's very slight, but there's a slight magnetic field to it. So whatever the case is, that when the moon goes to the center, the whole glass sphere goes to the center, or rises, and so that causes the relief in the pressure, and that's what causes the tides, because we get high tides during a big moon. I'm not going to say perigee or apogee, so I don't want to confuse you. We get high tides during a big moon, during a super moon, and even though the moon is farther away from us. Okay, so this is a huge revelation that's being disclosed to you. When I talked about the 22 and the 46 degree halos, that was, I put that video in private because it really doesn't matter. You can have whatever size halo. There's nothing special about that intersection. It makes much more sense for these glass spheres to be pulled in to actually conform to the phi spiral there and the phi spiral where it converges. So I brought in the two interior glass spheres, and it works perfectly with refraction and with the negative refraction zone of the moon sphere. So I think that's all I wanted to cover right now. But this is a extremely crucial revelation for you guys to understand what's going on. So, like I said before, I did a test orbit of Venus. Now, obviously, this is how the orbits work if you were to view one frame at the same time every day, every 24 hours. In reality, the planets are going to be moving counterclockwise. And so what I did, this is just to show the retrograde motion of the planets, which is not a literal going backwards. It's just simply the planets are slowing down or speeding up relative to the sun or to the celestial sphere. And that's what actually causes the apparent retrograde. It still is an apparent retrograde, even though the Earth is not spinning, but it's only apparent because in all actuality, all the planets are orbiting counterclockwise from east to west, only varying in velocity. And so if you take a frame at the same time every day, you're going to track this backwards retrograde motion to it. But they're all fitting within the truncated orbit behind the sun, or like in Venus and Mercury's case, in front of it. Now you might ask yourself, well, if the moon is only behind one glass sphere, why would we get sometimes a double halo from a full moon, just as we do from the sun? Moon. Well, think about that. Think about what I've told you before, how the direction of light hits the moon. It curves around back. Remember, the moon is not self-luminous. It's receiving sunlight from the sun. It's receiving reflected sunlight. So if we go to my graphic here, and we start it back up here at the top, where the sun is emanating its light, and it's going around both sides, or more like in a 3D sense, more of a toroidal shape, but it's converging here at the Gegenschein, and the direction of the light it's going to be hitting both glass spheres. You see that? Interesting too, if there is some kind of wave cancellation in this zone, in this negative zone, and the light is hitting it like that, it's quite possible that this is how we get the darkness funnel in this zone here, where the light cancels out, the wave cancellation cancels out. We still get the illumination of the halo, and I guess around the edges of that we would still get the illumination of the second halo as well. But this area, I believe, is the void, is the darkness funnel. So keep that in mind as well. Also, a couple years ago, I made this video about negative refraction of the glass sky in the Libyan desert glass. They have found graphite ribbons, 50 to 50 nanometers thick. Graphite is a natural material and graphene is a man-made metamaterial. Both can create negative refraction. So that's very interesting as well. Also check out this 3D simulation that I made of an octahedron with volumetric lighting and these openings at the seams of these diamond panels. So the light is escaping at the seams and it's creating this wave interference. And so we have this cancellation zone, I guess, if you want to call it. Possibly that could be at play as well. I mean, that's how we're getting bending light in the first place. Light is in the earth. It's in a container. It's constrained. It's confined. It's being affected by the ether, by the wave cancellation. I mean, normally, yeah, sure. If light is not affected by some kind of constraining, containing object or medium, it would be straight. But light, I mean, the universe is only 8,000 miles wide, so keep that in mind as well. So, there you go. Big news, guys. And so, yeah, it looks like I gotta update my moon video. Fun. All right. Thanks for watching. And now you understand why the moon lies and why the moon is loony.